So again, I'm presenting Panagiota Boskou, who's interested in joining us for a PhD. Amazingly enough, on the BSc part. So I mean, tonight we will go out for dinner, and you can also be invited to join. Also to celebrate our recent achievement of having the first space institute, maybe even in Greece, right? I don't know, but definitely on Crete. And so Panagiota wants to sort of buckle the trend. Oh, one more astronomer. You're an astronomer? Great, cool. Oh, yeah, sorry, I didn't see you. So plenty of, I do apologize for insulting you. I'm so glad, I'm honored that you're here and listen to. Panagiota is thinking about buckling the trend. So we have now a new space institute here with lots of funding from the EU and the Greek state. But Panagiota wants to do the opposite direction. So I came to space through ultra-cold atom, and Panagiota was thinking about going from space to cold atoms, which I'm excited by the idea. So Panagiota has quite a bit of space experience from before. She was in the same project like you, right? Space Dot. Yeah.
But not the same project.
Not on the same project, yeah. But at least in the same thing. So the University of Thessaloniki has, amazingly enough, a fully grown space program. They're even sending satellites up. And Panagiota was part of one of the space teams there, but she's not going to talk to us about that. Then afterwards, she went to the university, to Paris, to the Polytechnique and which institute?
At the beginning in the Observatoire de Paris, Observatory,
okay. And
then in LPP.
Okay, that's cool. So we have.
But today I'm going to speak about LATMOS and Observatoire.
Different stuff. But actually, we have a lot of connections to the Observatoire de Paris and their metrology group and their cold atoms groups.
Oh, I see.
So we know them. I know them many years from back then when they did the big frequency chains. Good. So without further ado, Panagiota.
Thank you.
And I apologize, I have to sneak out in between because there's a 5 minutes election committee in position in which I have to show my face. What's happening?
Okay. So I know that we have a bit of a mixed background, so I'm going to try in the first part to give you a general understanding of the field of space plasmas, and then I'm going to speak a bit more about what I did. So what we're going to do is speak about space plasmas, how we have observed them in the past, and how we are thinking of observing them in the future. Now, plasmas are tricky things to measure. The word plasma itself comes from Greek, meaning creature, and it was given that name because in the beginning, when we were studying them, they seemed like they were almost animate, like they had a will of their own, because when we were probing them and trying to impose external fields, they seemed to react in a very peculiar way. So you can possibly imagine already how challenging it would be to measure such a thing, especially in space, such a bizarre creature. And I'm going to try to give you this feel of these challenges that we face by taking you in a journey starting all the way from the Babylonian era and seeing how we have come to understand some things that we know about space plasmas, get a feel about what we don't know, and see how we are trying to find out. And on that note of how we are trying to find out, I'm going to speak to you about a project that I worked on, which is developing a new method to detect the Earth's magnetopause. So, indeed, plasmas are tricky to measure, but we have been doing it for quite a long time, thousands of years before we named it, starting with the Chinese and some mentions of dark spots on the surface of the sun. The same with the ancient Greeks. We even had drawings of these peculiar dark spots before the invention of the telescope. And with the invention of the telescope, the easiest thing to observe is actually the sun due to its proximity. So we start observing the sun, and this you could do also yourself. You could take a 5 centimeter diameter lens of very bad quality, put a mailing tube and project the sun into a piece of paper. And then if you do this about now and in the following years, you will start seeing these dark spots on your projection, and you start drawing them out and maybe documenting them. And this is exactly what Thomas Harriot did 2 years before Galileo. But Thomas Harriot has a very peculiar record of not getting scientific credit for what he does. So here I show you the pictures of Galileo that are a bit more popular. And then we continue building telescopes. And sorry, I want to check if the animation is, it's working perfect. So we continue building telescopes, we continue observing the sun, and we start noticing that there is a periodicity in the number of sunspots that we see. So what do we understand? That we understand what we don't understand, but we know that there's an underlying dynamic that governs this periodicity of 11 years. But what we do know is that there seems to be a connection between these weird things that are going on the sun and on the Earth. The best example of this is the Carrington event, where in 1859, Carrington is studying the sun, and he notices a very abrupt increase in the brightness of the sun. So 16 hours later, we have the strongest geomagnetic storm known in history. And telegraphs are burning up, sparking. If this was to happen today, all electronic devices here would go dead. And we have aurora in very low latitudes, and we don't really understand what is going on still with auroras. Why normally do we see them in high latitudes? Why are they called the northern lights? But we do know so far that there is a connection between this sun system and things that happen in Earth. And to understand better the aurora, a Norwegian scientist says, okay, what I think is going on, and we have this precipitation, we don't know yet this precipitation, these lights in the polar regions, is that actually we have charged particles that are shooting into the dipole of the Earth, and that's why they turn towards the polar regions. So to prove this, he makes an experiment. He puts a metal ball with that is a dipole, and shoots electron at it, and indeed is able to replicate the polar preference. So he says there must be particles shooting out of the sun. But at that point, we don't really know what is going on with the sun. So we go back to the sun and we try to understand what's going on. But now it's the 1930s, so we have a bit more knowledge about fundamental physics. We have a bit more tools to be able to explain things. And we also have spectrograms of the sun. So we take a spectrogram of the sun, and we understand that actually it seems to be ionized. Ionized meaning that it's a ball of charged particles. So what we will later come to call a plasma. We also say, okay, maybe we can see a bit part by part of the sun. Maybe we can obstruct the main source so that it doesn't blind us, and we just look at the corona, at the atmosphere. And we do that, and we realize that the temperature of the corona is extremely high, millions of degrees Celsius. So we do some calculations. We have these charged particles that are highly conductive, that are very hot. And if we do some calculations, we realize that actually the corona should extend way further beyond the orbit of the Earth. So what is going on? Are we swimming into the sea of the atmosphere of the sun, basically? And about the same time, we have people studying comets. And we have Biermann, who is studying comets, and he starts to notice that the tails of the comets are having a very preferential direction. So you have normally sometimes two tails in the comets, and he sees that one of the tails seems to always go radially outward of the sun, no matter the direction or the velocity of the comet. So he hypothesizes that, again, there are shooting particles out of the sun. So what is going on? Do we have shooting particles? Do we have sea of the corona? He discusses this with Parker, and Parker says in a conference, and Parker also discusses with Chapman, and Parker says, okay, this can actually be the same thing. So he writes 4 lines of algebra, as he said, and he theorizes that there is no charged particles, there is no shooting out, there is no atmosphere, and the better way to think of it is outflowing gas, like the one that can go out of a nozzle and like gets accelerated into supersonic speeds. But this gas is also charged as electrons and protons and heavy ions. And when it gets accelerated, it is also magnetically connected with the sun. So as it moves forward, it pulls also the magnetic lines of the sun. And as the sun rotates, this starts creating a twisting, like a dress of a ballerina, what is later come to known as the Parker spiral. So that's a wild claim to make, but also quite not so wild given these observations. And if we are to trust him a bit more than his reviewers, who suggested that he should go back to a library and read before trying to write a paper on it, what model will we create for the system? We will create the model that the sun is a rotating ball of charged particles, so we have magnetic fields. And in the beginning of the cycle, we can say that this magnetic field is perfect dipole, but then as the sun rotates, the equator rotates a bit faster. So we have magnetically connected lines with the plasma, and the plasma is pulling these lines and twisting and turning and creates weird magnetic configurations. That then these weird magnetic configurations are the ones that create these dark spots on the surface of the sun, because they're not really dark. They're just lower temperature because they have higher magnetic activity. So we have all this phenomena going on, and at the same time, we have this supersonic flow that is constantly going out to the sun. But at the same time, we have these configurations that are so complicated that sometimes they can stretch so much that they will break and reconnect with other lines, a phenomenon that is known as magnetic reconnection. And this is a very prominent accelerator in our solar system that we don't really understand yet. And we have this ejection of mass, known as a coronal mass ejection, for example, something that happened. It's very energetic. It's what in the end was the Carrington event as well. So you have all this system, very dynamic, very coupled with each other. And at some point, it will come and it will meet the Earth's dipole. What will happen? It can compress one side, it can elongate the other, moving all the way up to the moon. And if we think a bit better, oh yes, this is from Soho, some observations of very energetic coronal mass ejection, and also magnetic reconnection that happens in the Earth's magnetosphere in these types of events. But let's go back again to the solar wind. We have a supersonic flow that meets an obstacle. What happens in hydrodynamics when this happens? We create a shock. But now we have collisionless plasma, and also we have a shock. So this is a bit tricky. We don't really understand this fully yet. But indeed, we are able to, we get a shock that we name the Bose shock, with a supersonic flow meeting the dipole of the Earth, and the plasma gets decelerated abruptly, it gets deflected, but some of it passes through. And when it passes through, it gets very thermalized, very turbulent, very dense inside the magnetosheath, until it reaches a point where it comes into pressure equilibrium with the plasma that we have inside the magnetosphere of the Earth. What is the magnetosphere? It is the region where the magnetic field of the Earth is dominant compared to this interplanetary magnetic field that Parker was talking about. So basically what happens is that the dynamic pressure of the solar wind gets into equilibrium with the magnetic pressure of the magnetosphere of the Earth. And this boundary we call the Magnetopause. In that boundary, we can no longer mix and match plasmas of the solar wind and the magnetosphere. But now you will notice that if we can no longer mix and match plasmas, there is a bit of a gap there. Because I talked to you about auroras and how we have particles shooting inside the atmosphere of the Earth. So how do we get auroras if we cannot get particles from the solar wind inside? So a bit more complicated stuff happens over there because we have a discontinuity if we solve for this equilibrium between the two flows. And at the same time, this is not enough. We have this weird configuration of the interplanetary magnetic field that can come in contact with the magnetic field of the Earth, can break again lines, can do again magnetic connection, but at this time in the magnetosphere of the Earth, accelerate particles, precipitating them into the atmosphere. And this is still stuff that we don't really understand fully. And in general, don't ask a space physicist for the polar cusps and what happens there. So this is still complicated stuff that we don't understand. And as you've seen, we have made this assumption that the solar wind exists and supersonic, and we are left with a very complicated image of the structure of the magnetosphere. So we have to be a bit more convincing than saying that it could be a solution to both our problems. And the solar wind, we were quite lucky in this regard because it was the first time in astrophysics where we had so fast verification of our theory because of the Cold War, because everybody was rushing to throw spacecrafts into the air. So we had Luna 1 that measured the first supersonic ions, which was proof that the solar wind, there is indeed a supersonic flow. And we had this confirmation by Mariner 2 and a lot of other spacecrafts. And you may notice now that in order to measure this, it wasn't a remote measurement. We had to actually go there, trap some particles and measure their energy. So that's a bit challenging in the sense that you cannot easily remote sense. What you can do in plasma is measure particles, you can measure waves, and in some exceptional cases, you can measure light. So this is the tricky part of measuring plasma, and to give you a better feel of what this means is that basically we have this complicated structure that I talked to you about, the magnetosphere. And what we're trying to do is like trying to measure a river that is constantly changing, and we're closing our eyes, we're putting our finger inside, and we're moving it into random places. And then from this, we're trying to reconstruct every eddy and every turn and every twirl that the river takes. This is what we're trying to do. And actually, this is exactly what we do in the end. So what we are doing in order to understand, for example, if all of these things that I told you about the magnetopause and the Pose, and that we have some boundaries separating the plasmas, how do we know that this is true? We shoot satellites, basically. We take measurements, and in these boundaries, we will have some abrupt changes in some of the quantities that we measure. We will have some different characteristics in each parameter of the plasma. And here I show you an example. For example, here our satellite from the cluster mission is in the solar wind. Here you see ion measurements and the energy of the ions that we measure. So we have a very particular energy to our ions. This means that we have basically a beam that is traveling towards the Earth. We cross the boson. We have an abrupt change in velocity, for example. We cross the boson, and now we have thermalized turbulent plasma. So what we get is a very distributed energy, let's say, to a lot of energies, and we have a lot of thermal ions. And as soon as we cross the magnetopause, where we have this continuity in the density, because the plasma is no longer mixed, we have low energies, low density, everything is quiet inside the magnetosphere and well protected from the solar wind. So we take these crossings, we take thousands and thousands of them, and we try to make statistical models of the shapes of these boundaries. Here I show you, for example, the simplest model being the shoe model, which is just a parabola rotated. And this is quite tricky because the solar wind, as you've understood, changes all the time, is very dynamic, and with it changes all the structure of these boundaries. So we are trying to parameterize it compared to the conditions of the solar wind upstream, and we're trying to make this statistical analysis and crossing by crossing understand what is going on with the shape and position of the magnetopause, for example. And now the idea is, what if we could remote sense it? What if we could take actual pictures of this surface that is so dynamic? So to try to answer this, we went a bit back to comets and tried to get inspiration from this. And in comets, we had noticed that the heavily ionized heavy ions of the solar wind sometimes interact with hydrogen. They steal an electron into a high state, a high energy state, they de-excite it to a low energy state, and they emit an X-ray photon. And we also thought that inside the magnetosphere, we don't have any heavy ions from the solar wind. Inside the interplanetary medium, we don't have a lot of hydrogen, but in the area just between the magnetopause and the magnetosheath, we should have a good density of both. So we could possibly get this X-ray, charge exchange X-ray emission of a distinct area near this magnetopause that we could try to image. And this is exactly the premise of the SMILE mission, which is an ESA mission and the Chinese Space Agency mission that is going to be launched actually in less than a month, in 19th of May. And we'll try to image exactly this phenomenon. So we are going to go in a polar orbit around the Earth with an X-ray imager on board. And so because we haven't ever done this before, we have done a lot of simulations in order to understand what we could possibly see when we go up there. The LATMOS team, that was the one that was working on, created the LATEP model, which is a test particle model. What does this mean? We make some simulations using magnetohydrodynamic equations. We compute electric and magnetic fields, and then we take these fields and we put them as input into these test particles. So we have some fields, we launched heavy ions into these fields, and we calculate basically their equation of motion. So we calculate the motion of heavy ions in the solar wind, and then when they meet a hydrogen, we compute their emissivity, which is dependent on the flux of the solar wind, on the density of the hydrogen, on the atomic parameters of the reaction. And we construct these emissivity tubes. And in order to build now our actual images, we have to take particular orbits, particular positions of the spacecraft, looking directions, and then for each pixel, integrate over these emissivities and construct a simulated image that looks like the one on the right. So we do that to construct our images, but now what information do we get from these images? Like this, basically nothing. So we have to think of ways that we can use now this 2D information to derive information about the 3D shape of our magnetopause. And what I focused a bit more was a tangent fitting approach, which takes a big hypothesis saying that the maximum intensity arc that I see in my image will be the one of the tangent direction to the magnetopause. So now this takes some underlying hypothesis that is basically that I have a homogeneously emitting surface and that I have a surface that is semi-spherical. Otherwise, if I have very abrupt changes, I do not have this phenomenon of stacking a lot of little parts, let's say, that will contribute at the end to this high intensity at my image. And we will see that this will be a problem later. And if this hypothesis is correct, and in the places that it's correct, then we can develop a pipeline in order to derive parameters of empirical models by taking just as input a single image. So first part, tangent hypothesis, and if it's correct. So what I did was basically try to extract a ground truth about my simulation, where the magnetopause is, project this into the imager of the satellite for each position and each looking direction, and then compare with the maximum intensity arc of the simulated images. Here I show you just to get a feel of the SHU model that it has just two parameters, and I tried in the beginning to fit this to just my zero emission contours where I would suppose that my magnetopause is. And I show you because I wanted to see that the SHU model itself was constructed by equatorial measurements alone. So it cannot have any capability of describing the polar cusps. And then for the polar cusps, we have even more complicated issues, as I will tell you after. But basically, the model itself is incapable of describing such a shape. So it is a first good proxy, especially for the subsolar distance, which is how far is this point that connects to the sun. But it is not good to describe the shape of the magnetopause. So then I try to find other ways to extract that. And I could have taken, for example, the open to closed field lines. Open lines would be the magnetic lines that connect to interplanetary space. But that would be computationally more difficult. So what I did was just work with the emission tubes, take the maximum intensity for each radial direction of the, starting from the Earth of the emission tube, because this would theoretically be the point where I would have my magnetopause. However, the polar cusps are again a problem because the polar cusps are a region of very high emissivity, but without being part of the magnetopause, because the polar cusps are a kinetic effect and the magnetopause itself is a more magnetohydrodynamic effect. So we are trying to mix theories here that do not really go with each other. So I tried a bit to discard them, let's say, and try to keep only the emissivity from the magnetopause. I construct a good enough, let's say, surface, and I project and I compare. And for the summer orbits, actually, I get pretty good results. Like, it seems like we have pretty good results and that our hypothesis is working. When we enter the magnetopause, which is this image over here, we see absolutely nothing, and this is normal because in order to have a tangent, we have to be actually outside of the surface. But we have some failed cases. So in the summer orbits, we only have failed cases when we are way towards the sun and we have contribution from every part of the magnetopause, and then we cannot detect the arc because there's no very particular arc that we can detect. It's a smudgy thing. In the winter orbits, we have more complicated issues. First, the cusps. And this is a problem of how we extract the magnetopause and how we define the magnetopause. Because if you ask a lot of people that are working with cusps, how do you define it and how do you choose basically where it ends, you will have a lot of trouble getting a definite answer because we don't really know yet what is going on exactly, and this is why we're studying it. So this is one problem, and the other problem is that we have a severe underestimation of the tangent direction in the winter orbits, and this happens because two reasons. One is simulation, second is inherent to our hypothesis. So the simulation part is that in winter months, the orbit is such that we are not constantly, a lot of the time in the night side, which means that when we have simulated only the day side, and we cannot integrate emissivities over this part, of course, we are going to introduce a lot of errors. We are not going to add the emissivities from the part that we should be adding. And the other reason is that the subsolar point, having higher density in solar wind, emits a bit more than the rest of the magnetopause. So basically, this hypothesis that we took, that we have a surface that emits homogeneously, is not really true. So we will always have, especially in these angles, we will always have an underestimation of the tangent direction as soon as we cross the night side. And this you can see also as soon as we cross and go to the night side, we have a spike in error. But in the day side, this method works pretty well. This hypothesis works pretty well, and we can work with that. So we say, okay, for the summer orbits, we can work with, and we can create a very robust method in order to be able to detect the shapes all the time. So here in these images that you see, background noise will be added, instrument noise will be added, so it will become way more complicated in the actual picture to get an understanding of this arc. So it's not good enough to just say, okay, what is the maximum pixel? So what we do is we construct a set of magnetopause models from an empirical model that has parameter R0 and alpha, which is the subsolar distance and the flaring, how big or small it is. We construct a set of those, we project them all to the imager, and we take the mean intensity for each projection, integrating over the actual picture. And if we go to R0 and alpha space, then our most prominent integration, our highest mean intensity over a particular line, will correspond to the line that is actually the most, to the projection of the empirical model that is the most prominent in the actual image. So we test again, and we get pretty good results. But this is not what I'm most excited about, the fact that we get good results. What I'm most excited about is this picture, because our empirical model, as I told you, cannot describe the cusps. So this part over here, it cannot describe it. And this empirical model we constructed from these crossings that I told you about. And in this image, the only input that we have is this empirical model that we're trying to fit. And the magnetopause itself and the maximum intensity is the white line. So we could have, not in a month, we also need to actually calibrate the satellite and all the stuff. But when we actually get the pictures from SXI, we could have a method to characterize how good empirical models constructed by satellite crossings are in the global picture, like a shape, not particularly depending on the solar wind parameters. And this I'm really excited about because it doesn't depend on the simulation, it doesn't depend if you've modeled something correctly. And this is something that is very important because if you depend a bit on your simulation to tell you what is wrong with your physics, you're using already the physics that you assume. So this I'm very excited about to see in a few months, I hope. And then we did some tests with the dynamic case, where we took some simpler geometries and we took electric and magnetic fields from a real-life coronal mass ejection event. And we're trying to see if our method holds, and we have pretty good accuracy. But here we're stealing a bit because we don't have the weird viewing angles of the satellite. But we did it also for the case of another mission that's going to go into the moon, to try to do the same thing. And here we just show the limitations of the shoe model very clearly, because as soon as we have some different parameters, the model is fitting the cusps instead of fitting the actual magnetopause. So this is a clear limitation that the model itself cannot describe this type of geometries. So launch 19th of May, and we will find out if we have good empirical models, if we have good shapes, and if our physics works. Thank you.
Questions?
Yes.
This was all based on, this was all simulations that you showed this, or is it actual data?
No. It hasn't flown yet. So the images that you show, that we show, it's purely simulation, and we will. We don't use a data set. We use So basically, this that I show you here, we start by actually simulating. So the MHD model, it was already given, and not given. It's an open source model that you can run if you have a strong computer. So this simulates the electric and magnetic fields and the dynamics of the plasma that we talked about, all the solar wind, how it reaches this dipole and how it interacts with it by solving some equations, basically. And then using that, you just take single particles, charged particles, you put them in these particular fields, and you solve their equation of motion. Why don't you do it directly of taking particles and solving for the fields and sort for the particles at the same time, because it's a very coupled system. So the charged particles move, they change the electric fields. The electric fields, magnetic fields change, then the particles move in a different way. So it's a very coupled system, which means a huge ton of computational power. So you try to do tricks in order to reduce this computational power. And a test particle model actually it has kinetic effects on the ion scale. What does this mean? That if you take an MHD approach, you do not really get a good information about effects like the polar cusps, because these are include phenomena that MHD cannot describe. So if you care about the kinetic effect of a particular species, for example, ions in this case, then you should probably add then a test particle model approach to your MHD. But you can do MHD as well only. Yeah, okay. So yeah, everything is simulated here. And hopefully we will get actual images to compare soon. Yeah. Yes.
Sorry, again.
Yes, of course.
About the satellite, how is the satellite going to actually take the data? Because I saw at the simulation that it's going to be taking images.
Yeah.
So it's going to image what?
Exactly this. So that's the tricky part. So when I said that it's tricky to get information from these images, is that it's not image of an object. It's an integration basically of all the emissivity. Sorry. So basically, this part of the magnetopause will emit, let's say, isotropically to all directions, and this part as well, and this part as well, and this part as well. You have an imager that basically grabs all this X-ray light and integrates it here. So how can you basically taken out one dimension? You have taken out of the 3 dimensions and you have integrated into 2, and now you need to somehow reconstruct the 3D shape again, and this is the tricky part. The other thing you could do is tomography. So you could take a picture here, picture here, picture here, and try to reconstruct the surface, but then the surface is changing all the time. So you would basically lose the dynamic part you want to get from your method of remote sensing. And then other thing you can do is, I don't really like this, but is make a lot of simulations, and then use maybe some image detection in order to say, okay, this simulation corresponded to these conditions of the solar wind, and it looks like this that I'm seeing on the image. So maybe I have these conditions of the solar wind. I don't really like this because it assumes that your simulation is already perfect. And if your simulation is perfect, why are you sending a mission? So this is why I liked a bit this agnostic approach. Yeah. Yes.
I missed the beginning of your talk, but I'm wondering what is creating the X-ray emission? Is it only charge exchange, or you're using other components?
The emission is charge exchange between the heavy ions of the solar wind and the hydrogen in the exosphere of the Earth. We have some other contributions. So we have background also from the stars, but we have in general background emission that people are working on in order to subtract from the images. But yeah, this is the mechanism that we are trying to capture.
Okay, and then the second part of the question is, there's a lot of question about the physics of the charge exchange. I mean, we don't know the rates very accurately. We don't know what is really going on. So is this factor of uncertainty taken into account in the analysis?
It surely plays a huge, because you're basically simulating it. So it plays a huge role in the sense of how what you're going to get in your simulations. But in this that's why I liked this particular method, because this method is very agnostic to all this. The only thing that it assumes is that you will have the maximum emissivity where you have the maximum density of hydrogen and the max overlapped with the maximum flux of solar wind. This is the only thing that it takes as input. So it does not really care if you did the simulation correctly, because at the end it's not going to use the simulation. The simulation is just a proxy to test geometries. You could easily just make a dummy magnetosphere that is a sphere and that is weird shapes that we have never seen before, and still test the same hypothesis. And maybe you could do it better.
What I mean is that the composition matters. So if the particles are stratified in some way, then you may get, and some particles give you higher emission than others, have higher emissivity than others, then you may see an offset. So how sensitive would you be on that?
Okay, yeah. So that actually, I think they're trying to use it in the sense that there will be different channels for different ions. So you will actually be able, hopefully, to see.
Band imaging in multiple bands.
Yes.
All right. Okay.
Yeah.
Okay, good.
So actually, this is also a very interesting thing, that you will be able to see each ion, how far it goes. That's very interesting.
Maybe one last question. So you told us about this trying to map this magnetopause through X-ray emission. Is there other way to do that? Are there other projects trying to do the same
Through X-ray emission?
No, exactly. Is there any other way of trying to map the magnetopause or try to infer the geometry of the magnetopause?
The classical,
not using the X-ray.
The classical way, exactly. This is exactly what I meant here. The classical way is just crossing it with satellites. So I cross the magnetopause here. I detect this jump in density. So I know that here at this point of time, I've crossed this boundary. And now if I have thousands of satellites and I can get thousands of these crossings, then I can do a statistical analysis to reconstruct a bit this shape. But as you understand, when this thing is constantly moving, actually you could have a satellite that is moving, and then you see 10 crossings like this at a time. This is because the surface itself is moving as you have a dynamic solar wind event. So you're here, you're traveling, and the surface is doing this, and it's doing an oscillation. So you understand that this is very dynamic. So it's very difficult to make this statistical analysis of just single point measurements. And that's why I gave the example with putting your finger and checking, because this is exactly what you do. Single point measurements, you collect them in years and years, and you try to make a shape out of it. It's a bit complicated. It works, but we would love to have a more global view, let's say.
Okay, thanks. Any last question? No, then let's thanks our speaker.